In this video, we want to prove that Q is denumerable, and Q is the set of all rational numbers like 1 over 1, 1 over 2, 1 over 3, anything with an integer in the numerator and the denominator, so 2 over 3, negative 3 over 4, whatever. And recall that being denumerable essentially just means that it is countable and infinite. Now, essentially, to be countable, essentially what that means is we can have a mapping from the natural numbers. There's actually a more formal definition. We can say that a set A is denumerable if and only if the cardinality of A is equal to the cardinality of n, where n is the natural numbers. That being said, the natural numbers is infinite. So for example, if we wanted to get all the set of odd numbers like 3, 5, 7, 9, and so forth, all the way up to infinity, we can simply map it by taking, this is our natural set, and this is our set A, which is going to be these odd numbers. We can simply draw a mapping from 1 to 1, 2 to 3, 3 to 5, 4 to 7, 5 to 9, and we can create a formula that will give us that input and output. And conversely, we can map backwards, where we can go from A back to n, using the inverse of that formula. But if we look at something like the set of integers, where we have a whole bunch of negative numbers, all the way to negative infinity, all the way up to positive infinity, in order to map the natural numbers, which begin at 1 and go up to positive infinity, we could draw a mapping like from 1 to 1, 2 to 2, 3 to 3, 4 to 4, and so forth. But then we have all these negative numbers over here, and we can't really count those. But the sort of solution here is to change the way that we're writing the set of integers. Instead of writing it like this, what we can do is we can write 0, 1, negative 1, 2, negative 2. And then we can, do the mapping like this. 1 to 0, 2 to 1, 3 to negative 1, 4 to 2, 5 to negative 2. And there's a formula for this. It's not that complicated, but the general idea here is that the reason it wouldn't be countable if we did it this way is because we would be going toward infinity. And if we had an infinite amount of time, we would never get to these numbers over here. So if we change the way that we're mapping them in an order that makes sense, then therefore, so what we do is guarantee that if we had an infinite amount of time, we would be able to map all of these natural numbers to these integers here. Now the question is, can we do that with the set of rational numbers like 1 over 1, 2 over 1, 3 over 1, 4 over 1, etc.? And the answer is yes. What we can do is we can kind of construct a table like this where it's 1 over 1, 2 over 1, 3 over 1, 4 over 1, and then we just repeat that all the way up to infinity, all the way up to infinity over 1. So just imagine, we have a continuation going on here. And then we do the exact same thing but with the denominator. Here we're going to have 1 over 2, 2 over 2, 3 over 2, 4 over 2. But essentially we fill out this whole thing and imagine that this table, goes to infinity, right? Down here we're going all the way from 1 over 1, 1 over 2, all the way to 1 over infinity. And then over here we're going all the way to infinity over 1, infinity over 2. Here we're going all the way to infinity over infinity. Just imagine that this table, continues what it's doing to an infinite degree. And then when we map it to the natural numbers, we just count everything in a snake-like pattern. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, so forth. And that way we make sure that we're going to hit every single number, and if we had an infinite amount of time, we would be able to count all of the rational numbers. And that's basically it. That is the proof that Q is denumerable.